In this module, we're talking about the physical properties of air, which is covered by Chapter 3 in the textbook. Any substance has a set of intensive state variables that describe its essential properties under specific conditions. Examples include pressure, density, or a specific volume, which is just the reciprocal of density, temperature. For air, humidity would be a state variable, and there's salinity for seawater, which affects density. The relevant state variables for any particular substance aren't free to vary independently, but rather are linked. For example, most substances expand when heated. That is, their density decreases when their temperature increases. Another way of looking at that is that their specific volume increases. Also, most substances respond to increased pressure by becoming denser or more compressed. This effect is very pronounced for gases and is much less so for solids and liquids. Variations in composition may also be relevant. Humid air is less dense than dry air at the same temperature and pressure. Salty water is denser than fresh water at the same temperature and pressure. In the ocean, in fact, variations in salinity can sometimes be more important than either temperature or pressure in determining seawater density. For most substances, and by that I include air, seawater, ice, metal, granite, lots of other things, there is a predictable relationship between state variables. It's often possible to write a mathematical equation that governs this relationship. Such an equation is called an equation of state. The validity of any equation of state is usually restricted to a particular range of conditions. So, for example, we are going to be concerned with the conditions that exist in the atmosphere and not consider air that is under extremely high pressure in a tank or something. Three early scientists contributed the essential insights that led to an equation of state for gases under typical conditions of pressure and temperature. There was Robert Boyle, who was an Anglo-Irish philosopher, chemist, physicist, and inventor. He's regarded as one of the founders of modern chemistry. Jacques Charles was a French inventor, scientist, mathematician, and balloonist. Lorenzo Romano Amadeo Carlo Avogadro was an Italian scientist most noted for his contribution to molecular theory, now known as Avogadro's law. So Robert Boyle performed careful experiments that demonstrated that the volume of gas held at a particular temperature is inversely proportional to pressure. For example, doubling the pressure reduces the volume by half. Mathematically, Boyle's law can be written as V, the volume, is equal to some constant C1 divided by the pressure. So if the pressure goes up, the volume goes down. C1 is a constant that depends on both temperature and the composition of the gas. Jacques Charles is credited with finding that the volume of a gas at constant pressure is proportional to its absolute temperature. For example, a gas at 300 Kelvin that is heated to 330 Kelvin while keeping its pressure constant will increase in volume by 10%. 330 degrees Kelvin is 10% hotter in absolute terms than 300 Kelvin. Mathematically, Charles' law can be written V equals C2 times T. V is the volume, C2 is again a constant, and T is the absolute temperature. C2 is a constant that depends on both pressure and the composition of the gas. It's really important to note that this relationship does not work if you try to use temperature expressed in Fahrenheit or Celsius. For example, if you used Fahrenheit and put in a temperature of 0 degrees Fahrenheit, this relationship would incorrectly tell you that the volume is 0, even though you're far above absolute 0. So be sure to use Kelvin whenever using a proportionality between volume and temperature in Charles' law. Lorenzo Avogadro found that equal volumes of gases under the same conditions of temperature and pressure will contain equal numbers of molecules. Mathematically, this can be written V, again that's the volume, equals C3 times N, where C3 is a constant that depends on temperature and pressure, and N is the number of molecules, usually expressed in moles or kilomoles. 1 mole represents a number equal to Avogadro's number, which you might remember, again, from chemistry as 6.022 times 10 to the 23rd. We will often use kilomoles because we're working the SI system, in which case a kilomole is 6.02 times 10 to the 26th molecules. Boyle's law, Charles' law, and Avogadro's law can be combined into a single universal equation of state for gases called the ideal gas law. And it reads as follows: P times V equals nR star times T, where R star has the value shown there, 8,314.5 joules times kilograms to the minus 1 and kilomoles to the minus 1. That's the universal gas constant. That's valid for all gases that obey the ideal gas law. The pressure, as before, is P, V is the volume, N is the number of kilomoles, and T is the absolute temperature. Any gas that obeys the ideal gas law is by definition an ideal gas. The ideal gas law is an accurate equation of state for any gas that satisfies certain conditions. One condition is that the effective combined volume of the molecules in the gas must be very small compared to the total volume of the gas. What that basically means is the space between the molecules has to be much larger than the size of the molecules themselves. They can't take up very much of the total volume. The other thing is that the average spacing between the molecules has to be large enough so that, on average at least, the attractive forces can be ignored or neglected between them. To satisfy these conditions for most gases, pressure can't be too high and temperature can't be too low. Air at atmospheric temperatures and pressures obeys the ideal gas law well enough for almost any practical purpose. There are more accurate laws than the ideal gas law that can be used when needed for high accuracy. We're not going to have to worry about those in this class. To recap, the version of the ideal gas law that you may have seen in chemistry is PV equals nR star T. P is the pressure, V is the volume, N is the number of moles or kilomoles if we use SI units, R star is the so-called universal gas constant, and T is the absolute temperature. R star has a value of 8314.5 joules per Kelvin per kilomole. And the question is, why does it have those units? And specifically, why are joules in there? Let's look at the left-hand side. P has units of pressure, so it might be expressed in pascals, which is newtons per meter squared. The volume, V, has units of meters cubed in SI units. So the product of those two on the left-hand side is going to cancel two of the meters and give you an overall set of units, newtons times meters, which is the same as a force times a distance, and that has to be an energy, which is measured in joules. So that's where the joules come from in this relationship. So for that reason, R star has to give joules when multiplied by kilomoles and Kelvin, which cancel those units, leaving only the joules. Now we want to look at how to adapt the ideal gas law to atmospheric applications. The version we already looked at is the one usually used by chemists and chemical engineers. There's a couple of things about that version that are not quite friendly for use in meteorology. First of all, we don't like extensive units. Volume V and kilomoles N are both extensive units. They depend on the size of the sample, the system you're working with, the size of the parcel, the size of the container that you have air in. We don't like extensive units. We're going to want to work with intensive units. We'd also rather work with mass, or even better density, than with the number of molecules or moles. And one reason why we're willing to do that and prefer to do that is because we're not going to be dealing with a variety of different substances. We're going to be dealing with basically two cases, dry air and humid air. And so knowing the density is about as good as knowing the number of molecules or moles per unit volume. We can always convert extensive units to intensive units by dividing by mass. So starting with the original form of the ideal gas law that we've already looked at, we can divide by m, capital M, the mass, on both sides. So we have P times V over M equals N over M times R star times T. That V over M is just the specific volume. It's the volume per unit mass. So we've converted the extensive volume V to an intensive specific volume alpha. On the right-hand side, we've taken the ratio of the number of kilomoles to the number of kilograms, which is basically kilomoles per kilogram. But if we take the inverse of that, that becomes kilograms per kilomole, which is just the molecular mass of the gas. And that little m represents that molecular mass. So we take the reciprocal of that to represent N over capital M. Now we take R star divided by that molecular mass, and we call it just R. So the final version that we have here now in intensive units is P alpha, where alpha is the specific volume, equals this new constant R times T. That's the version that we just saw. Alternatively, we could also write it as P equals rho times RT. Again, all we're doing there is using rho in the equation instead of alpha. Alpha is specific volume, rho is density. One is just the reciprocal of the other, so we can either put it on the left or the right-hand side of the equation. And again, R is defined to be the universal gas constant divided by the molecular mass for the specific gas of interest. So R is not universal, it's specific to a particular gas. If the gas isn't a mixture, but consists of just a single component, like pure nitrogen, then the molecular mass is just the standard molecular mass for that particular gas or component. So for example, nitrogen has an atomic mass of 14, and there's 2 atoms per molecule, so the molecular mass is 2 times that, or 28. Oxygen is 16 times 2 for a total of 32 for the molecular mass. To recap, here's one form of the ideal gas law. It's just P alpha equals RT, where R depends on the gas we're considering. If the gas is not a single pure gas, but rather a mixture, then the gas constant R is not given by R star divided by a single specific molecular mass of one constituent like oxygen or nitrogen, but rather we have to use an average or mean molecular mass for the mixture, and that average is going to depend on the relative proportions of each component. Specifically, what we want to do in atmospheric science is determine the appropriate value of R for dry air. And so we need to first determine what we're going to call the mean molecular mass MD for dry air, and the corresponding value of R we're going to call RD, the dry air gas constant, which will be defined as R star divided by the mean molecular mass for dry air. So how do we determine that dry air gas constant? We need the mean molecular mass of the standard mixture of gases in dry air. Recall that the molecular mass, or the mean molecular mass, can be thought of as just the total mass, m, in kilograms, divided by the total number of kilomoles for that gas. For just 2 gases, for example, the mean molecular mass is given by the sum of the masses contributed by the 2 different constituents, capital M1, capital M2, divided by the total kilomoles contributed by each gas, N1 plus N2. And that mass in the numerator can be expanded as the product of the molar contributions times the molecular mass. So N1, little n1 times M1 is a number of kilomoles times a number of kilograms per kilomole And so that product has dimensions of mass, or kilograms. And the same for the second constituent. If we have more than two constituents, then we just have to generalize to a sum of that type right there, where you take as many constituents as you need to take into account, and you figure out their relative molar contributions and their corresponding molecular masses, and calculate that average. In fact, if we divide by the top and bottom of the total number of moles, which would be the sum in that denominator that you see there, then we can really even simplify things down to express the mean molecular mass as just the sum of the individual molecular masses weighted by their molar fraction or their volume fraction, because the two are really equivalent. You've seen this table in Chapter 1, which is just a table of the major constituents and minor constituents of the atmosphere, including their fraction by volume, which is the same as the molar fraction. So the middle column there is what we really need to tabulate the contributions that these gases all make to the mean molecular mass. We're going to ignore water vapor because it's not part of dry air, so we just cross that one off the list and we focus entirely on the more or less permanent constituents. And we also ignore some of the trace gases like nitrous oxide and carbon monoxide, because the amounts that they're present are so small that they really don't change the mean molecular mass in any way that matters for us. So once we do that, we can trim it down, at least as kind of a first cut, to this table of major constituents. And I've only listed 4 here for simplicity. We've got nitrogen, we've got oxygen, argon, and carbon dioxide. And in the middle column, I have the molar fraction or volume fraction of each one. You'll recognize 78%, or about 78%, as being the number for nitrogen, 21% basically for oxygen, almost 1% for argon, and then about 400 parts per million for CO2. The corresponding molecular masses are in the right column in kilograms per kilomole. And we see roughly 28 for nitrogen, roughly 32 for oxygen, roughly 40 for argon, and about 44 for carbon dioxide. If we apply the formula that I just showed you with the summation to those values, then we get a mean molecular mass for dry air of 28.9655. Now, that's more precision we really need, but better to have a little bit and drop it later than to have too little. So that's what I get directly from my calculator. Now, to interpret that number, look at where it falls between the two major constituents, nitrogen and oxygen. Nitrogen is a little more than 3/4 of the total, and it has a molecular mass of 28. Oxygen is a little less than 1/4 of the total and has a molecular mass of 32. So you expect that the mean molecular mass is going to fall between those two and is going to be a bit closer to nitrogen than to oxygen. And sure enough, it's about 29 versus 28 for nitrogen and versus 32 for oxygen. So having determined MD, we now can divide that into the universal gas constant to get RD, and that number turns out to be 287.0 joules per kilogram per Kelvin. This is a number that we'll be using often enough that I'm going to highlight it here, and you'll certainly know it by heart by the time you've used it a few times. So to wrap everything up for dry air, we have this form of the ideal gas law, which is P alpha equals RdT, or alternatively, P equals rho RdT. Again, the only difference is alpha in the first case for specific volume, rho or density in the second case. Sometimes it's convenient to use one, sometimes the other. And as I said, RD has the value of 287.0 joules per kilogram per Kelvin in SI units. I'm highlighting them here because the above equations and the above value of RD are going to be used so often that you should probably just go ahead and memorize them now. These are really central to a lot of what we'll be doing for much of the semester. This version of the ideal gas law is what we'll reach for anytime we are not too concerned about the influence of humidity on air density. So just to reiterate, this is an equation that is valid for dry air, and we can use it anytime we're not too worried about the mild or minor effects that humidity will have on the gas constant. But we're going to come to that next. What is the density of air at sea level in the standard atmosphere? Now, the pressure at sea level in the standard atmosphere is 1013.2 hectopascals, which in pascals, SI units, is 1.0132 times 10 to the fifth. The temperature at sea level in the standard atmosphere is 15 degrees Celsius, or 288.15 Kelvin. Starting with this version of the ideal gas law, P equals rho RdT, because we want density, we solve for density by dividing both sides by RdT and get that rho equals P over RdT, and we can plug in the values of the parameters that we have above there and also 287.0 for Rd, and immediately get 1.225 kilograms per meter cubed. So that is the density of air at sea level in the standard atmosphere, just a little over a kilogram per meter cubed, almost 1.25 kilograms per meter cubed. What about air that's not dry? There are two different ways to deal with the common case that air is not dry, but rather contains some fraction of water vapor. One way, which is kind of the obvious way, we could compute a new mean molecular mass, and from that, a new gas constant, which we could call R humid, for example, instead of Rd for R dry. That's one way. And in that case, the ideal gas law would look like P equals rho times R humid times T. And our chore would be to determine R humid for each different case of humidity. Another way would be to keep the gas constant for dry air. In other words, don't use R humid, use Rd in the equation, but instead tweak the ideal gas law some other way to preserve its validity as an equation of state for humid air. Now, that sounds a little strange and convoluted and not necessarily the most obvious way to go about things, but it turns out that that's what we're going to actually do. Before we can tackle humid air, which consists of a mixture of dry air and vapor, let's take a look at water vapor all by itself. Let's consider vapor which is not mixed with air. It's just pure water vapor somehow in gas form with no other constituents. If we treat it as an ideal gas, we can write the equation of state as follows. E equals rho v RV T. Now this notation looks funny because you haven't seen the E before, but this is really the same ideal gas law, but we're using some new notation. We're using E to represent the pressure of the water vapor. This is a standard notation for just pure water vapor. We're using rho v as the vapor density, also known as the absolute humidity. And then RV is the gas constant for pure water vapor. And of course, T is still the absolute temperature. Now, water has a molecular mass, MV, of 18 kilograms per kilomole. And so we can immediately find the gas constant for water vapor, RV, by dividing the universal gas constant, R star, by that MV to get RV is 461.5 joules per kilogram per Kelvin. Now, like the other version of the ideal gas law, this is very fundamental. We've got an expression for the relationship between vapor pressure and vapor density at a specific temperature. And we have a gas constant for water vapor, RV, which applies only to pure vapor, not to a mixture of vapor and dry air, only to pure vapor. Now that we've looked at water vapor by itself, we want to return to what happens when you put different gases together that have their own pressures. And this gives this gives us occasion to look at Dalton's law of partial pressures, which you might remember from chemistry. A convenient feature of an ideal gas consisting of a mixture of different component gases is that each one obeys the ideal gas law separately. So for example, if we have two components with gas constants R1 and R2 respectively, then for the first one we can write that its pressure, P1, is equal to its density, ρ1, times its gas constant R1 times temperature. And for the second one, same thing. The pressure of the second constituent is equal to its density times its gas constant, and again times temperature. The two pressures individually are called the partial pressures of each gas. And the total pressure is just the sum of those two pressures. So P1 plus P2 equals the total pressure P. And if we substitute the two forms of the ideal gas law shown above and separate out the temperature, we get an expression that looks like that. We have ρ1 R1 plus ρ2 R2 all times temperature. And of course, you can generalize that result to any number of components. If you had 10 constituents, you basically have to set up the ideal gas law for each one with its own gas constant, and then you can sum all of the individual pressures to get the total pressure of the gas. Now let's apply Dalton's law to humid air. The total air pressure can be regarded as a sum of two components. The contribution PD from dry air and the contribution E from water vapor. So the total pressure, P, is now PD plus E. We can expand those components using the ideal gas law for each component. And so the total pressure then becomes the density of the dry air times the dry air gas constant, RD, times T, plus the density of water vapor, or absolute humidity, times the gas constant for water vapor, RV, times T. And it's not possible for the two constituents to have different temperatures, so we can factor the temperature out and write that the total pressure is equal to that quantity in parentheses, ρD RD plus ρV RV, all times the absolute temperature. So continuing, let's carry that over, the same equation that I just spelled out, and we start with that. We can now multiply and divide the right-hand side by the total air density to get the following. So if you look at that carefully, we've got a row that is multiplying the whole thing on the outside, but then inside the parentheses we're also dividing the other rows, ρD and ρV, by rho, the total density of air. And so we're multiplying and dividing by the same thing, so the equation is equivalent to the one above. And we can do the same thing with RD. We can pull RD outside of the parentheses by multiplying and dividing. And we have now that the pressure is equal to rho, the total density, times RD, the dry air gas constant, times that quantity in parentheses, which involves ratios of densities, dry air to total air, density of water vapor to total air, and also the ratio of the gas constants, RV to RD. And everything in parentheses is now times the absolute temperature. Now let's carry that last form of the equation to the top and continue. We can now take the density rho and expand it as ρD plus ρV. And by doing that, it allows us, for example, to say that ρD inside the parentheses is equal to rho minus ρV. So we can write the equation as seen there. And if we take that first ratio, rho minus ρV divided by rho, and factor or divide rho into the numerator, then that becomes 1 minus ρV over rho, and then we have an additional term plus ρV over rho times RV over RD. You'll notice that the ρV over rho appears in two places, so we can factor that out, and now we can write that everything inside the parentheses is just 1 minus the quantity RV over RD minus 1 times ρV over rho. So hopefully you can verify that I did the math correctly, that this is right. And we'll now take that last version of the equation and carry that to the next page. And there we have it again. So now we want to define a new quantity that we will use often. So this is not just being done in passing for this one equation. It's the ratio of the molecular mass of water to dry air. And we're going to call that thing epsilon. And it's defined as the molecular mass of water vapor divided by the molecular mass of dry air. So numerically, it's 18.01 for water vapor divided by 28.97 for dry air, and it has the value 0.622. Let's also remember that RV, the gas constant for water vapor, is R star, the universal gas constant, divided by the molecular mass of vapor, and RD is R star divided by MD for dry air. So that ratio of the gas constants is really just the ratio of the molecular mass. So RV over RD is just MD over MV, which is the reciprocal of epsilon, and it has a numerical value of 1.61. Again, carrying that last version of the equation to the top, we can then simplify the above to the following. P equals rho RD times 1 minus 0.61 times rho V over rho times T. So things are looking a little simpler now, and we're getting closer to where we want to be. We're not quite done, but we're getting close. We need to take a brief detour and introduce some more variables related to atmospheric humidity. These are key humidity definitions, and they are ones that you should memorize. We already mentioned the absolute humidity. It's just the density of water vapor, rho V. Another way of expressing humidity is the so-called specific humidity, which is defined as the ratio of the mass of water vapor, MV, in a parcel to the total mass, M, of air in a parcel. It's really the mass of water vapor per unit mass of air. And it's defined as follows. We use a Q to indicate this ratio, and unfortunately Q is used for other things in this course as well, but from the context you will usually be able to tell whether we're talking about humidity or something else. So formally Q, the specific humidity, is the mass MV of vapor divided by the total mass of air, and if you multiply top and bottom, or divide top and bottom by V, it's really the same as the ratio of the densities. So the density rho V divided by the total density of air. A closely related variable is the water vapor mixing ratio, W, which is defined as the ratio of the mass of water vapor, MV, to just the dry air mass, MD. So previously we looked at the ratio MV to just M, which is the total mass. Here we're looking now at the ratio of MV to just the dry air component of the mixture. And so that turns out to be useful in certain contexts that we'll look at later. And that is, again, equivalent to just the ratio of the densities. In this case, the density of vapor to the density of dry air alone. So both Q and W, the specific humidity and the mixing ratio, they're both dimensionless ratios of two masses. So if you specify them without any other qualification, they're really just numbers. They have no units. But normally in meteorology, we tend to use units of grams per kilogram. And it's still dimensionless. It's still a length divided, or it's still a mass divided by mass, but it's numerically different in the sense that a pure ratio of 0.01 is really the same as 10 grams per kilogram, because there's 1,000 kilograms. There's 1,000 grams in a kilogram, so 10 grams per 1,000 kilograms is the same as a ratio of 0.01. So if you're given a value of 0.01 for Q, then you can think of that as being equivalent to 10 grams per kilogram, or vice versa. If you're given 10 grams per kilogram, you're going to have to convert it to the dimensionless ratio in order to use it in a calculation. Now going beyond that, it can also be shown that there are exact conversions between specific humidity and mixing ratio. And I'm not going to go through them here. You can look at them on page 74 of the book. But basically, the mixing ratio is equal to the specific humidity divided by 1 minus Q, and the specific humidity is equal to the mixing ratio divided by 1 plus Q. Again, using the dimensionless ratios, not the values with grams per kilogram. Because if you try that with grams per kilogram, you'll get nonsense. Under normal atmospheric conditions, both Q and W are numerically much less than 1. So the following approximations are usually good enough for this class. The exact conversion, as we showed a moment ago, between W and Q are given by the equality on the far left there. But if you look at Q as being numerically small compared with 1 in the denominator of that expression, then it really becomes negligible compared with 1, and that ratio just becomes very close to just Q by itself. And likewise, if you look at Q as being equal to W divided by 1 plus W, but W is small, very small compared with that 1 in the denominator again, then again, that ratio really boils down to just being approximately W. So as a result, we can usually get away with saying that the mixing ratio W is numerically about the same as the specific humidity Q. And it's not very common that we have to worry about the small difference between those two quantities. It's nice to know the definitions of each and the exact conversions if you need them, but normally in this class we're going to be able to treat the two as being approximately interchangeable. So finally, and this is kind of important, it's sometimes or often necessary to relate the specific humidity Q or the mixing ratio W to the vapor pressure E, which we already looked at. Again, on page 74, it's shown that these are approximately related to each other in the following way. W, which is the mixing ratio, is approximately equal to epsilon times E divided by P, which in turn is approximately equal to Q, the specific humidity. The E you'll recognize as the vapor pressure. Epsilon you'll hopefully recognize by now as the ratio of the molecular mass, 0.622. So now we're going to go back to the ideal gas law for humid air and clean up and finish up the steps that we were going through before. We left off with this relationship right here, and we want to further simplify it down. Let's look at that rho v over rho inside the parentheses, and if you recognize that ratio from what we just talked about, you'll see that that can be replaced by the variable Q for specific humidity. And so we can simplify that expression down to the following. We now have a version of the ideal gas law that looks like this. The pressure is equal to the density times the dry air gas constant times this term involving 1 minus 0.61 times the specific humidity Q times the absolute temperature. And that is an exact expression for or an exact version of the ideal gas law for humid air. But we're not quite done yet. There it is again, just for reference. And as I mentioned before, there's two ways we could treat the term in parentheses. We could either interpret the product of that with RD as an adjusted gas constant R humid for humid air, and that would actually be correct. So if we do that, then we've got that the pressure is equal to rho times R humid times T, where R humid is now defined to be this RD times the correction term involving humidity. But that's not what we will normally do. Instead, we will take that 1 minus 0.61 Q and multiply by T and call that thing a virtual temperature that accounts for the effects of humidity on air density at a given pressure. So we define the virtual temperature as follows. TV, the virtual temperature, is defined as 1 minus 0.61 times Q times the absolute temperature. And then the ideal gas law for humid air can be written P equals rho RD TV. This formulation, both formulations, allow us to continue to use the familiar dry air gas constant RD while still correctly accounting for the effect of humidity on air density. Danger. If given a specific humidity Q in grams per kilogram, you have to remember to convert it to a unitless ratio before plugging the value into the formula. So you just have to divide by 1,000. So for example, if you're given 20 grams per kilogram, it becomes 0.020, which you can then plug in for Q in the definition of virtual temperature. And the other thing that, again, I'm mentioning because I've seen it done wrong many times, you have to use absolute temperature in both the ideal gas law and in the calculation of virtual temperature. So here's an example. What is the density of air at sea level in the standard atmosphere if it has a specific humidity of 25 grams per kilogram? This is just like the problem we already looked at for the ideal gas law for dry air, only we're adding a humidity of 25 grams per kilogram. Again, the pressure at sea level is in the standard atmosphere is 1.0132 times 10 to the 5 pascals in SI units. The temperature is still 288.15 Kelvin. Now we also have Q of 0.025 because we've converted the 25 grams per kilogram to the unitless ratio. Plugging that into the expression for the virtual temperature, we have that the virtual temperature TV is equal to 1 plus 0.61 times the 0.025, all times T, and that turns out to be 292.5 Kelvin. So the real temperature in this case is 281.15 Kelvin. The virtual temperature is a couple of degrees, in fact about 4 degrees warmer. It's 292.5 Kelvin. And so the resulting density then is the pressure divided by RD for dry air divided by the virtual temperature TV, and plugging those numbers in we get 1.207 kilograms per meter cubed. Now that density is about 1.5% less than we had previously found for dry air at the same temperature and pressure. So the effect of that added vapor is to make the air lighter, to make it less dense than it would have been dry at the same temperature and pressure. And that 1.5% is really coming from the difference between the virtual temperature and the absolute temperature. The virtual temperature, 292.5, is 1.5% larger than the actual temperature of 288.15. Okay, there's a couple of points that are very important to learn concerning virtual temperature. The first is that the difference between real temperature and virtual temperature TV is usually pretty small, typically around a couple of degrees, or in percent terms, around 1%, or even much less in drier air. It's not usually a large correction. For that reason, we can often ignore that difference and just use temperature to calculate air density from the ideal gas law. So if you're given information about temperature but not about humidity in a problem, for example, or on the quiz, then you can probably just get away with using the temperature and your result is going to be accurate enough, unless I give specific information that leads you to understand that a more accurate calculation is needed that takes into account the humidity and the virtual temperature. So there are certain situations in which higher accuracy is important, in which case we do have to use the virtual temperature. It comes into play when you're looking at the buoyancy of a parcel in the atmosphere, when you're trying to calculate the height of a pressure surface based on a sounding of temperature and humidity below that level. Another important thing to keep in mind is that virtual temperature has nothing to do with heat index. We're correcting the temperature to take into account humidity, but it's not in any way related to comfort or the kind of thing we usually associate it with mugginess. It is only meaningful as a measure of the effect of humidity on air density. To summarize, and this is going to capture the most important points from this lecture, the ideal gas law for air is given by P alpha equals RD TV, where alpha is the specific volume, P is the pressure, RD is the gas constant for dry air, TV is the virtual temperature. An equivalent version of this expression or this equation is that P, the pressure, is equal to the density, rho, times RD TV. And the virtual temperature is given by TV equals the sum 1 plus 0.61 times the specific humidity Q, all times the absolute temperature T. And Q, the specific humidity, is related to, it's about the same numerically as the so-called mixing ratio W, but more importantly, it can be computed from the vapor pressure E by taking epsilon times E divided by the actual pressure. And again, Q is the specific humidity, W is the water vapor mixing ratio, P is the pressure, epsilon is that ratio of molecular masses which has the numerical value 0.622. This slide right here captures the most important parts of Chapter 3 that will become super central to much of what we do for the next few chapters.